All right, students, let me try another one here. There's a question about number 62 in chapter 20. And the problem goes like this. It says the inside of a hollow cylinder is maintained at a temperature of TA while the outside is at a lower temperature. All right, so they have this cylinder. And the cylinder has some, thickness to it. It's hollow on the inside. They're saying the temperature on the inside is TA. And then on the outside, the temperature is TB, because they're saying that the radius of this cylinder has a inner radius of A and an outer radius of B. And to me, this kind of looks like maybe hot water in a pipe. So we kind of have this internal water here that is at a temperature of TA, and maybe a hot water tank, actually. And so we're trying to maintain this at a hot temperature. And then there is a temperature on the outside. And so if your hot water tank is, say, in your garage, then we would have then a flow of heat energy through the container of the hot water tank. And there would be a certain rate of flow. So it would be losing heat. And that's why you would have a little flame under here. And so after the water warms, even if you don't use any hot water, it's eventually going to cool down until the flame goes back on, and burns some gas and warms it up, okay? Okay, so it says here the wall of the cylinder has a thermal conductivity of K. So there's K. Ignore the end effects. Show that the rate at which energy is conducted from the inner to the outer surface is given by this equation. All right, so what I'll start with is this equation. Here's what we learned in class, that the rate at which energy transfers per time would be equal to a negative K times the area times what we call the temperature gradient. And so this was worked out and thought about in the simple case. The simple case being a rod, let's say, where the temperature on one side and the temperature on the other is, well, I'll call it temperature 1 and temperature 2, but the difference is that D or delta T. And then this is the length of it, or the dx. Okay, and the A is the area. That's the one I really want to focus on here, because that's going to have the biggest effect when we get to something that's not quite so uniform in diameter here. In fact, let's take a cross-sectional look at this. If here's the inner circle and I have some hot water at temperature A, as it's flowing outward, you might say there are these layers, if you will. I'll make a dotted line. Whereas the energy flows out, since the circle is getting bigger, the area that it flows out is getting bigger. In fact, I'm thinking maybe you can see this best with a kind of a sticky note here. If I kind of wrap this originally kind of tight, okay, so that the heat energy is inside here and flowing out, it's got to flow out through an area that is represented by this sticky note. So it would be the circumference and the length of it. Okay, now a moment later, after it goes through the first layer, it would have to go through a second layer. Now that second layer has a slightly bigger radius, and therefore it has a slightly bigger area. Of course, then as it goes through the second one, it's got to flow through the third one. This is kind of fun. And maybe I'll do one more just for my fun here, but I can do a fourth one here. Okay. And what I'm going to eventually get is a hollow cylinder that's got some thick walls. But we call this the shell method, if you will. And so it's got to flow first through that cylinder, then through that cylinder, then through that cylinder, and then through that cylinder. And each one has a slightly bigger radius here. And that's what I'm trying to show here in kind of this three-dimensional picture, but I hopefully these came out on camera a lot better, kind of showing that the heat is flowing out and the area is getting bigger because the circumference is getting bigger. Now, obviously all four of them have the same length, but this one here, it's got a bigger area because it's got a bigger circumference than the first one, which I believe was that one. Okay, and so the tricky part here might be this area, but I'm hoping you just saw in my little construction of sticky notes here that the area then would be the circumference 2 pi r times L, where I didn't put it in my diagram, but it's in the problem diagram. They call that capital L, the length of it. Okay, so there's the circumference, and then there's the length, and then there is the dt d. And maybe then, just to make sure we're kind of understanding, this is the x. It was derived as the direction or the flow of the energy. In our case, it's going radially outward, so we might as well call that the r, and it would fit with that r, and so we might as well make those match. But that's kind of important that you recognize that this is the gradients of the temperature. So in this case, the gradient is radially outward and not in a linear x direction like derived in class. So that might be the tricky part about that, is making sure you can convert then a dx to a dr and understanding why we did that, as well as convert the A into the area that it is conducting out and realizing that it begins to change. Now, there is perhaps one more tricky thing here, and that is to recognize that this number, dq dt, would be a constant number. Let me just call it P, since it does represent an energy per time. It's a rate at which thermal energy, and usually we call energy per time power, so although usually that's mechanical power, but I'm going to just call it a P for power. This is the flow of heat, and so if we're maintaining the inside at a constant temperature, then as the energy flows, whatever flows through the first layer then goes into my second layer, which then goes into my third layer. Oh, I might have got those out of order now. What order were these? So this looks like the smallest one. So it'd flow first to that one, then to this one, then to... Don't know if I can get these back together. So what order were these? Was it like that? Something like this? Ha. And like this? Yay! Okay. So it's going to be flowing through this layer first, okay, then this layer, then this layer, and then this layer. But when steady state is reached, there is no more increase or decrease in temperature. And so as the energy is flowing, there is an equal in compared to an equal out. And so what flows through one layer is equal to what flows to the next layer, which is equal to what flows to the next layer. And so that's why this dq dt has nothing to do with where you are on here. It is a constant value. Of course, you can kind of see, to be a constant value for bigger r's, you would have to have a smaller gradient. But that is perhaps the tricky part of this problem. Okay, I'll say it again. The three tricky things are, number one, recognizing that this is the area that the heat flows through with the corresponding dr. Okay, that's the second thing. And of course, the third thing is right there, recognizing that this only makes sense when that number is a constant. And since this looks like a derivative to me, I'm going to write it as a P so I don't get myself confused, because now when I look at this, I just see math here and I see a differential equation. I see two variables. I see a T and an R. And you've heard me say this a couple times, so I'm going to say it again. But you ever have an equation that's a differential, the first thing you should always look at is it separable. And in this class, they're all separable. You know, we're not trying to give you anything harder than the easiest differential equation. That's a little too premature for your math level. So we have a lot of separable, and this one is definitely separable. You can kind of see that if I move maybe the dr and the r to the other side, I get dr over r on the left-hand side of the equation, and I'm left with just t on the other, and then a bunch of constants. And you can decide if you want to put the constants together on the right or the left, or leave them separate. I usually put my constants together, but you know what? I'm just going to leave them separate. So the negative k 2 pi l I'll just leave alone, and the p I'll leave alone, but I will put the r on the left, and the t is already on the right. Because now, this is the whole point of the separational variables, is you can integrate both sides. So in this case, if we start from the inner part, we would be starting at a temperature of TA and going to the outer part, which is a temperature of TB. So there's the limits of the temperature. And the limits of the radius, as we said back here, would be from the inner radius A to the outer radius B. So this would be from A to B. And so if we actually do this integral, we've got the p, and then we've got the integral here of dr over r. Well, that's the natural log of r, evaluated from A to B. These are constant, so it's minus k 2 pi l. And then, of course, the very easy integral, the integral of dt is just t, and then evaluated from tb to ta. All right, so then we can finish by saying this problem is asking us for the rate of flow. So let's solve this for this p. I suppose maybe now we'll just write it back to a dq. We only did that just to kind of help us realize that wasn't part of the differential equation. It kind of looks like a derivative, but that was not the thing that changed. It was the temperature and the radius that was changing, not the heat per time. Okay. And then maybe to make it look like their answer, I'll move the negative sign into here. So this becomes a k 2 pi l, and then we get ta minus tb to change the order. And then we can then divide that by the natural log of b over a. Yay! And so there it matches their answer. So the rate of flow, either into or out of, I thought of it as out, so hot on the inside flowing out of a cylinder.